represent the fungal growth velocity (CFU) through the simulation, conclusion, and suggestion action. In conclusion, this graph proves the ground rate peak around the 36 hour with the higher expected velocity. Therefore, the system provides yearly warning that silo recovery action, such as drying or temperature control, must be implemented before that critical period in order to meet the quality of the country price. That is, thank you. Detailed graph analysis. Based on the computer simulation display, this graph divided the analysis into response age well y-axis again time in kilo, 72 hours. First, fungal biomass curve, solid orange line. Axis reference left y, axis curl 0 to 55,000 CFU. Graph behavior according to the logistic ground model from hour 0 to 24 ground is slow leg pace. From hour 24 to hour 44, ground increase sharply, exponential pace. After hour 48, ground begin differ from level of centenary pace, approaching the maximum capacity limit value at 50,000 CFU. Number 2, ground damage velocity curve, t-shirt red line. Axis reference, right y-axis curl 0 to 2,200 CFU. Graph behavior from a bell curve graph. It measures the rate of change of acceleration of fungal ground at each specific hour. Number 3, critical peak point. Location at hour 36. Mathematical analysis at hour 36. The t-shirt red line. T-shirt is higher peak velocity value reaches almost 1,900 CFU in calculation concept. This is collect the inflection point of the original function, where the fungal inflection rate separate the faster across the store timeline. That's all for me.
Hi everyone, my name is NURUL binti Muhammad Zahir. My number matric AX25A1778. And today I will be present about the interactive lipid dynamic curve. This topic is related to the accumulation of lipid or biomass in plants after analysis, which is the FAWWAZ stage. The graph shows how the whole quantity is over time and how fast the accumulation occurs. The bioscience problem study in this graph is called lipid or biomass in plants throughout the developmental stage of discovery. In bioscience and biotechnology, biomass production is very important because it can be used in production of cosmetic and biofuel processes. Therefore, scientists need to determine the next period for lipid accumulation in order to maximize production efficiency. This graph helps us understand the relationship between the screen time and the rate of whole accumulation in plants. Study is important because it play a major role in energy storage and biofuel production. By understanding this graph, scientists can determine the optimal capacity time, improve biofuel production, and reduce waste of resources. Furthermore, studies like this also support the development of more efficient and environmentally friendly agriculture techniques. This graph contains two main curves. Green curve is totally whole percent. The green curve represents the total amount of biofuel accumulated over the width of the analysis. At the beginning, the oil content is still very low. Then the graph increases rapidly around width 12 to 13. After that, the increase becomes slower until it reaches nearly 16%. This shows that lipid accumulation becomes very active during the middle stage of plant development. Orange curve is accumulation rate. The orange curve represents the lipid accumulation rate or how quickly the oil is introduced. at the early stage, the accumulation rate is low. Then it increases animation speed around bits 16 to 70. After that, the rate gradually decreases. This means that bits 16 to 70 are the last active period for lipid production, and after this stage, the plant still produces whole but at slower rate. The relationship between these two curves is very important. When the lipid accumulation rate increases, the total or percentage also rise rapidly. However, when the accumulation rate starts to decrease, the total or graph begins to stabilize. For this class, from this graph, we can conclude that there is an active phase of lipid accumulation followed by a maturation phase where accumulation slows down. One recommendation to improve this HTML is by adding clearly interactive labels, more contrasting color, and automatic explanation when users click on a point in the graph. In addition, developer can include animation or pop-up data display to user can better understand the change in value for each bit. In conclusion, the graph helps us understand the pattern of lipid accumulation in plants after increases. Studies like these are important in bioscience because they help improve bio-oil production and support the development of more effective agriculture. Thank you.
My name is DANISH and today I will present my project title, Application of Directive in Agro-Product Technology using Mango Drying Process. This project shows how directive in calculus can be applied to real food processing situation in Malaysia. Drying is an important process used to reduce moisture content, preserve food quality and extend shelf life. Bioscience problem. Mango is widely produced in Malaysia and is often dried using hot air drying technology. During drying, moisture content decreases over time. Industry need to control the drying rate because drying too fast can damage food quality, while drying too slowly increase cost and processing time. Graph an interactive feature. The graph shows that moisture decreases rapidly at the beginning and more slowly over time. An interactive chart graph allows users to click on point to view the moisture content, reactive value, and simple explanation of the drying rate. Importance of directive. Directive help industry optimize drying efficiency, reduce energy consumption, maintain product quality, and improve process control. Conclusion. In conclusion, this project demonstrates how directive can be used to analyze the mango drying process. The mathematical model and interactive graph help visualize the rate moisture loss and show the practical application of calculus in agro-product technology.
Assalamualaikum. My name is FAREEZ ZIKRI bin KHUSAINI. My metric number is F2582092. Today I will present our project title, Oil Palm Yield Analytics. This project applies calculus concepts, especially function and derivative, to analyze the productivity of oil palm plantation over time. Our objective is to determine how oil palm yield change with plantation age and identify the most productive period for harvesting and replanting decision. For the bioscience context, in Malaysia, agro-industry oil palm is one of the most important agricultural crops. The production of FFB, fresh fruit bunch, directly affects the profitability of plantations. In this project, the function fx represents the oil palm yield in tons per hectare per year, meanwhile the derivative fx represent the rate of change of the yield. Plantation managers can identify the point where production starts to decline and decide the best time for replanting. For the mathematical modeling, this equation models the growth and decline pattern of oil palm yield over time. The derivative measures how quickly the yield is increasing and decreasing at a specific plantation age. For the graph analysis, we can observe that the green curve represents the absolute yield Fx. The orange dashed curve represents the rate of change Fs. Initially, the yield increased rapidly during the early years of plantation growth. The derivative reached a high positive value, indicating strong growth. After approximately 13 to 15 years, the yield reached its peak at around 33 tons per hectare per year. After this point, the derivative becomes negative, meaning the yield starts to decline gradually. For example, at 25 years, the yield is approximately 29.5 tons per hectare, while the derivative is negative, indicating decreasing productivity. And the conclusion, this project demonstrates how calculus can be applied in agricultural technology. The function fs help us predict oil palm yield, while the derivative fs help us understand changes in productivity over time. By analyzing these mathematical models, plantation managers can make better decisions regarding harvesting strategies and replanting schedules. That's all for me, and this is the end of our presentation. Thank you.